Hello, welcome to virtual tour of focused ion beam scanning electron microscopy lab. I'm Katherine Dovidenko. I'm the director of Nanoscale Characterization Core, and we have multiple interesting techniques and approaches to get analysis of materials and devices. I'm self-recording the video, and that's why I'm not wearing a mask, because otherwise I cannot speak loud enough, and I don't think anyone would be able to hear me. So this is our scanning electron microscope, focused ion beam microscope. It has multiple very interesting attachments that allow us to do more detailed analysis. Materials analysis can show us topography, can show us morphology, can show us what the material is made of. If we take an example of, let's say, iPhone, there are multiple different materials that are utilized to make the iPhone. So case would be made, for example, from some aluminum alloys. Electronics has very, very different set of materials, and more interestingly, device properties that are needed for device to function. So here we can put our material or device of interest inside of the scanning electron microscope focused ion beam chamber, which is this big front door that you can see in the front of the instrument. We do the analysis while our material or device is under vacuum. And once the material is analyzed, we can take it back out. The analysis is done and recorded through the computers here. So here on the screen, we have an example of only one of multiple materials that can be analyzed. Here we have an image of a packaging foam. It's a regular packaging foam that can be put under the microscope and imaged under certain conditions. It's a non-conducting material, so in this case we're using a special function of this particular model of the microscope, which is low vacuum, or actually a little bit higher pressure. We add a little bit of water vapors inside the chamber, so we could image a non-conducting material like this. The scale bar on the screen right here is 200 microns. So you can see a magnified image of a styrofoam. Let me show you some close-up images. Continuing, showing you what we can see through the electron microscope. On the screen here, you see 4 different images. The image on the bottom, if I magnify it, is showing us what's going on inside the chamber of the microscope. This is where our sample is, and that's where the electron beam is coming from. The imaging in the electron microscope is formed by rastering the electron beam over the surface of the sample in the scanning electron microscope, or putting the electron beam through the sample in transmission electron microscope. This is our scanning electron microscope. So here, the beam of electrons will be coming out from the lens, through the lenses of the microscope, onto the surface of the sample, rastering on the surface of the sample, generating secondary electrons, which are then captured by one of the detectors that we have in the chamber, or we can introduce into a chamber, and getting the image. So now, here would be an example of our image. We are looking at the same foam that I have just described. Here is an image of that packaging foam. A very small piece is taken away and placed inside the microscope. You can see that this bar is 500 microns. Just in comparison, this is about 5 to 10 times larger scale bar than the diameter of a human hair. So we can also do something else with our materials here. We can do so-called focused ion beam microscopy. In this case, inside the same chamber, we also have a second source, which is a source of gallium ions. The gallium ion beam is also getting onto the sample surface, and in the case of gallium ions, it's not only generating the secondary electrons or secondary ions, which can be used for imaging, but it is also capable of removing material. In this image here, what we see is the result of rastering or scanning the ion beam inside this area and selectively removing this material, if we would have continued cutting more and more of material out, almost like making a trench, we would see a nice cross-section and we would be able to see what's going on under the surface of our material. And we can do the same with the devices. Here on the bottom quadrant, this is a camera looking top down on our sample. So the foam, I'm not sure if you can see clearly, but the foam is right here. This is the piece of this particular foam. Also, we can use two attachments to the microscope, which allow us to do EDS, energy dispersive X-ray analysis, which shows us what the material is made of. And we can also do EBSD, electron backscatter diffraction pattern analysis, which shows us the crystal structure of the materials right here, right under the same electron beam. Let's get some imaging. I will start the electron beam rastering on the sample surface. I will adjust the contrast and brightness a little bit for you to better see. You can see how the front moves across from top to bottom of the image. This is representative of how the electron beam rasters first from left to right, then steps down, left to right, and steps down again. And we're getting the image using the secondary electron signal. We can magnify, we can focus to get a little bit better image. The microscope is capable to resolve structures at nanoscale, so we can go to fairly high magnifications and resolutions. Let me show you one other type of images that I have here on the screen. These are polypropylene fibers that are part of N95 mask material. The project is looking at improving N95 mask material's properties, and we've been looking at some of the fibers and developing the conditions at which we can get optimal images of the fibers. If you have any questions, please don't hesitate to contact me, Katherine Dovidenko. I'm part of Center of Materials, Devices, and Integrated Systems, and Nanoscale Characterization Core is where our instrumentation is located. Thank you. Have a good day.